we're gonna have like 3 sections we're gonna go through today. We're gonna start with just like a sort of basic review of control theories. Oh yeah, so the name here, Nick Shuchuk, is actually one of the controls wizards that we have for like inside of Bronco Space, and so he put together most of this original presentation, and I am just kind of presenting in his steed. So here we go. We're going to go through first sort of like quick review on like what are control systems, how can you kind of classically model control systems. Then we'll talk specifically about like what options are available to you for spacecraft control systems. And then we'll go through a little design example at the end too. So let's just get right into it. First, what is a control system? For people who are like non-engineers, I think is actually something that is kind of hard to wrap your head around at first. But essentially, control system is like a system that has like an actuator, right? And it causes a vehicle to behave in a certain way based on an input from the operator. So in aerospace, we have like the ailerons, right? Like on the wings that produce control movements. Here in the back, like a background, this is like an RCS block. RCS being reaction control system. Usually these like shoot like little puffs of gas, right? That kind of spin the spacecraft around. But like also something like a robot arm, that's also a control system. And something like the gas pedal in your car, steering wheel, the thermostat in your house, pretty much anything that takes a human input and then causes a physical change in a physical system can be considered a control system of some sort. On spacecraft, we have 3 main ones, which are reaction wheels, magnetorquers, and thrusters, which we'll talk about some more later on. One of the things that is important to understand when you're thinking about control design is also block diagrams, because that's usually how you'll see these systems represented. Now, you don't actually need to understand so much for this purpose, like how to do like block diagram math or anything like that. But when you take your controls class in university, they'll probably have you go through this for like a couple weeks. But the important thing to understand is that most mechanical systems can be simplified to a point where they can be approximated mathematically. In this case, this mass spring system can be approximated with a sine or cosine function because it has a sinusoidal motion. And this is sort of the entire basis of how control systems are at least initially designed, right? You try to model the system mathematically, and then you try to analytically determine what you can change about it to get it to perform the way you want it to perform. So most of the systems that you learn in university, you're going to be dealing with second order differential equations. Don't worry too much about the math. We're not really going to do math during this presentation. But the important thing to know about second order ODEs is that they can be solved, right? And usually second order ODE is defined as a system that has 3 characteristics about it that change. And they can have less than 3, but if it's more than 3, right, then you're in trouble because that's a system that actually cannot be analytically solved. And there's a lot more complex math as to go into it. But examples of like a second order system are like a mass, a damper, and a spring. If you're an EE, something like a resistor, an inductor, and a capacitor might be more up your alley. But for the sake of like just basic control in satellites, oftentimes you can idealize the system as a mass damper spring system. Yeah, don't worry about the math too much. It's just kind of background. You can do all this fancy pants math, right? When you have like a transfer function and all that to figure out like the response of your system based on an input. So you have to remember, right? Control system takes a human input, right? You tell the system to do something, like if it's a thermostat, right? You tell it to go to a temperature, or your steering wheel. When you turn the steering wheel, you're telling the vehicle to turn some certain amount. And the control system is the interface between your input and the actual physical, thing, that action that manifests. And something called a transfer function kind of goes in between them. The transfer function is like, you put in like X at one end, and what you get out the other end, X is your input, whatever you get at the output is the output. And the transfer function with this fancy pants math can roughly idealize, right, like how the system's going to respond in terms of like rise time, like how long does it take to get to the value you wanted to get, like a peak time, right, like how long to get to a maximum value. Because sometimes, right, like you can have things like overshoot, undershoot, right, how long does it take to settle. Yeah, we'll get into this a little more. Not really, actually. One of the things that's kind of important to understand is transient response. Now, in aerospace, we usually actually use like a continuous time S-domain response. Um, Basically, what that is the system becomes idealized as a continuous function, right? Like a smooth curve, basically, right? Where all the points are connected to infinity. Real world systems behave in a continuous manner, but the computers that actually control real world systems are unfortunately discrete, right? It's all ones and zeros in there, right? And you can have really high resolution systems that behave essentially continuous, but they really aren't continuous. So when you get really into it, you have to actually discretize, right, all of your sort of equations so that they become little steps rather than just a continuous curve. But we're not going to worry about that too much for the sake of this like introductory workshop. Something important to understand, though, is that when you talk about control systems, there are sort of three types where you have like stable systems. And what a stable system is, you can see on this plot. Don't worry about like the position of the poles right now. But stable systems are systems where if you take your hands off of them and just let them do their thing with no intervention, they will eventually stop, right? Like they are just going to reach a value and they're going to stay at that value. That's a stable system. Then there are marginally stable systems. Marginally stable systems are systems that oscillate. So a marginally stable system will forever kind of like just bounce like in between a set of values rather than settling on a single value. And then you have totally unstable systems, right? Which are systems that you get it going and then it just keeps going forever. Like it never stops itself from, going in a certain direction. In sort of a rule of thumb is that the more stable a system is, the slower it is to respond to an input. And we usually call that damping, right? Like a very damped system is a system that is slow to respond to input, but you know that because it's very damped, that it won't just go nuts on you. And depending on the requirements of your system, you might want that, you might not want that. It really just depends on what you're trying to accomplish and how much you trust your control algorithm to sort of figure it out at the end of the day. I'm actually going to skip this. Okay, so control theory, right, is how we go about actually designing the system that turns your input into the desired output. And for the sake of what we're doing, pretty much everything we do is going to be a closed loop control system. What that means is that you have your input, right, your desired value that goes into the system. You have some sort of controller, right, that translates your input and tweaks it, right, so that when it's applied to the plant, which is your physical system, right? The plant in this case might be like the satellite or the robot arm, right? Or the steering wheel, the car, right? That has all of those physical properties about it, produces a desired output. And then the feedback part is that rather than just going straight through, right, from input straight to output, there's also a feedback where we take the output as it's happening and stick it back in the system, right, to adjust the response as the system is ongoing. There are also linear and nonlinear systems. We're not really going to get into nonlinear systems at all because they are very complicated and totally beyond the scope of an undergraduate program. And so we're going to just focus on like the linear systems for now. And you can generally idealize a satellite system as a linear system and pretty much get away with it, aside from like really precise, when you have really precise pointing requirements. Sort of a summary here, right, is that a linear system is one where the outputs and inputs can be added together and they can be separated. Whereas a nonlinear system, they cannot be added and they cannot be separated. What that sort of means is like the outputs and inputs being inseparable are when two physical characteristics of a system are coupled to each other. If I remember correctly, in spacecraft, you can sometimes get this thing known as a pitch roll. Is it pitch roll or is it pitch yaw? It's one of, I think pitch and roll are actually coupled if you have an unsymmetrical spacecraft, where you cannot affect one of those properties without it also affecting the other. Yeah. Flynn, were you gonna interrupt me or?
Nah.
Okay, we're good. Am I going too fast? I feel like I'm tearing through this, but yes, no, maybe. Actually, I think I can put the list of people over here. So if you guys want me to go slower or go faster, you can just hit the button. Okay. I'm getting a go faster, so I'm just gonna go faster. There's a closed loop feedback system. We already talked about that. Now, most spacecraft are going to just use normal PID control theory for the actual controller. You might also introduce things like Kalman filters on the discrimination side, but in terms of control, for the applications that a CubeSat is going to find itself in, PID does a pretty good job. And in fact, oftentimes you can get away with just a PD and forget the I entirely. As a quick review for people who have never seen a PID controller before, PID stands for proportional, integral, and derivative. And quick summaries are here, right? So the proportional controller just increases or decreases the magnitude of the signal that goes through the system, right? Think of this as the big multiplication sign. Gets bigger or gets smaller, depends on how the system is set up. Integral, right, accounts for how long an error has existed. So what that ends up doing to the system is if you have like a very small error, like you're just barely right, like off of the value that you want, and it's kind of just there, like your system settles at a value that is not actually the value you want. The integral gain, right? If you turn up the integral, it can get the system to the value you want. The problem is that integral can also introduce oscillation. Derivative, on the other hand, accounts for how fast the error changes. So derivative can smooth out the system if it is oscillating. The issue, though, is that derivative can also just slow down the system in general because it introduces damping. So it's sort of a balance between all these three values to get the value you actually want. Here's some other stuff where kind of what I was just saying, right? Like proportional amplifies the response, increases overshoot, introduces a steady state error, though. Integral can eliminate that steady state error, right? Like not being at the actual value you want. The problem is that integral causes oscillation. Um, Derivative, right, provides damping, um, but it slows the system down. So it's a balancing act between all of these values. Okay, so here we get into the actual process of designing a control system for a spacecraft. Before I go here, though, that was my rapid fire, like 15 minutes, an entire semester of control theory, just kind of shoved at you. Is everyone okay with what I just all went over? Like, there are questions. I can visit some questions right now, or if anyone didn't understand anything. All right, I have a thumbs up and a green check. So I'm just gonna say we're good and keep going with it. So I'm gonna take a quick drink of water actually. Okay, so you understand basic control systems now, or at least you're too confused to ask any questions. So we're just gonna go ahead and jump right in the even deeper end of the deep end and talk about how we actually put a control system on a spacecraft now. And for those of you who are not familiar with the SMAD, it is the Space Mission Analysis and Design textbook. The latest version is works at all 2011. I don't actually have my copy in my room right now to hold up for you to see, but it's like 1,100 pages worth of what can be considered the space mission engineer's Bible. Um, and the sort of process for designing an additive generation control system is actually described pretty well in the textbook. And here it is. There are 6 steps, and you're going to sort of iterate through these steps as you build out the system. So the very first thing you need to do, and the most important thing, is define your control modes. Now, what does that mean? This comes from an understanding of what your mission actually is. Just as an example, like say you have a mission that is Earth observing. So satellite has a camera, right? Now you have to ask, okay, what is the camera going to take pictures of? We want to take pictures of the Earth, right? Like just say we don't really care too much about like exactly what on the Earth we're taking pictures of. So the control modes are pretty simple, right? You have a control mode where the system is going to try to point the camera at the Earth. That's one of your control modes. Now, you also have to think about like, okay, is like, do I need the camera to be tracking an object on the Earth, or does it just need to be pointed in the general vicinity, right? And that kind of hones in what does the controller actually need to do? Another control mode that's really popular in spacecraft is a sun pointing mode, because it's very uncommon for CubeSats to have articulating solar panels. Moving parts and reliability don't really go with the whole low cost paradigm. Um, if like let's say one face of your satellite has a lot of surface area with solar cells on it, you might want a control mode where the spacecraft will make sure that face with all the solar cells is pointed perpendicular to the sun to get maximum power generation. Or you might have a mode where you have a patch antenna, which is a directional antenna, and that needs to be pointed at the Earth in order to actually send down all your data. So these are your control modes. You need to define what your control modes are first, because understanding what the control system needs to do is how you actually get down to selecting, what is appropriate to be on your control system. The next thing is you need to quantify the disturbance environment. This actually is not that important for CubeSats, because for a craft as small as a CubeSat, it is pretty inconsequential, assuming that you have a control system at all. Pretty much any control system will be able to overcome the disturbance environment. This is really only a big issue with like really big spacecraft. Like say you're like the Hubble Space Telescope with like huge solar arrays. atmospheric drag can actually be like a significant problem for you, right? Because those solar arrays act as massive, well, massive in quotation marks, drag sails. For CubeSats, though, they're so small, you generally can just get away with it. You don't have to worry about the disturbance environment so much. One thing, though, that you do need to remember is that the magnetic disturbance environment is oftentimes the worst one for CubeSats. Um, like especially if you have like anything that's magnetized or magnetorquers on your spacecraft, the magnetic disturbances can actually, there are known cases where magnetic disturbances have thrown CubeSats sort of really out of whack. One famous example that I always bring up is the Move 2 spacecraft from the University of Munich. They had a wiring issue that they did not know about. They didn't know it was going to be an issue before they launched. Essentially, what it was is like the wire that came from their solar panels into the spacecraft created a wiring loop. Well, it created a loop, right? The electricity flowed in a loop around this wiring, and that ended up creating a very weak electromagnet on the spacecraft that, when it interacted with Earth's magnetic field, caused the spacecraft to go out of control and spin up to a hilarious speed of 500 degrees per second before they were able to get it back under control due to some cunning control engineering. But stuff like that you have to watch out for. Next, you select the actual actuators, right? That go, you select the type of control that you use depending on the control modes. So in traditional spacecraft engineering, there are things like spin stabilization, right? And other, weird methods, yo-yo D-spin. You don't really have to worry about those because they're pretty far out there for CubeSats. But types of control that you probably hear a lot are things like detumble, right? When you first come out of the spring-loaded box, like your satellite is finally free and in space, oftentimes there's a little bit of tumble action going on there. Or God forbid, you're one of those poor CubeSats that gets just yeeted off the space station by a cosmonaut, right? Then there's a lot of tumble that you're gonna have to smooth out of the system before you're able to do anything else. So the control methods are, words like detumble, right, where we try to go from an uncontrolled spin to a stable, just we're vibing, right, we're just floating. There's no angular movement here. There are things like just normal pointing, right, where we just try to point at a target. There's also tracking, right, where like there's a point on the ground, for example, and as we fly over, we try to, follow that point with the spacecraft. Once you understand what your spacecraft needs to do, you can actually go to select and size your hardware. And we're going to do this portion. I'm just going to show you some stuff kind of live, actually. Oops, I mean to do that. I'm just going to kind of show you this live. So not sponsored by SAC-Search. They are they do have representative in the Blue Dot Consortium, but they did not pay us any money to use their website. I just think it's the most convenient. There, like I mentioned earlier, there are a couple different types of actuators that can be used in a satellite control system. Now, an actuator, remember, is the device, right, that takes the input and makes the physical change in the system. So we go in here to attitude, you can see actuators. There's three options here, but really like control moment gyroscopes are kind of the same thing as reaction wheels. The most common is magnetorquers. And I think the statistic is like 80% of CubeSats have magnetorquers now. What these magnetorquers do is they essentially turn your CubeSat into a compass. Magnetorquers are characteristically just either a coil like this, right? Just a literal coil of wire, or they are a rod, sometimes called torque rods, that are also a coil of wire, but they might have like an iron core in the middle. And what these are electromagnets. If you remember from your like high school AP physics class, right? You run a current through a loop of wire and it creates a magnetic field. And that magnetic field that's created can then interact with Earth's magnetic field. And that actually will create a torque on your spacecraft. Now, it's important to note that this is a torque, not a force, right? So magnetorquers cannot physically move your spacecraft like translationally. There's no forwards or backwards with the magnetorquer. There's only spin, right? And so it can induce a spin in your spacecraft, and that can allow the spacecraft to, say, from a spin, right? It can remove the angular momentum and detumble it, or it can, you know, slowly guide a spacecraft towards a pointing orientation, right? All by interacting with Earth's magnetic field. The pros of magnetorquers, they're relatively simple, right? It's literally just a coil of wire that you run a current through. So they're pretty foolproof and they're easy to implement. They're also very damped, which are um, depending on your system could be good. And what that means is that they generate such a small amount of torque that you move pretty slow with magnetorquers. So it's hard to screw it up, right? Like there's going to be no situation where you're just flopping out of control with the magnetorquer because the control system has freaked out. In fact, if the system gets stuck, right, like if the magnet is just always on, that can actually be good because then it just turns into a hysteresis rod. What a hysteresis rod is just a literal permanent magnet that just makes sure the satellite doesn't spin out of control because it's always trying to align itself, right, with the Earth's magnetic field. So it eventually reaches a state of stability. Hysteresis rods are kind of like don't do them in the CubeSat industry because a couple years ago, a couple CubeSats got stuck together because permanent magnets and lost both of the CubeSats. So yeah, but magnetorquers are becoming pretty commonplace. They don't actually have to even be like these independent systems. It's becoming increasingly popular to actually embed them inside like the solar panel PCBs as like just a really thick copper pour in the shape of a spiral. Those are magnetorquers. The others are reaction wheels. Reaction wheels are the more traditional way to have your spacecraft torque about. If you remember to your physics class back in high school, at some point your teacher probably had someone in the class sit on a rolly chair, hold a bicycle wheel right in their hands that was spinning, right? And when you hold it like straight up and down, no spin. When you turn it this way, right, like the magic happens, and then the angular momentum starts spinning you in the chair. Same thing basically with reaction wheels, where they spin in themselves, right? And when that spin speeds up or slows down, it transfers the torque from the wheel into the spacecraft, right, through the whole conservation of momentum thing. And so reaction wheels are great because they can move the spacecraft really fast. Like they can be pretty snappy. And they can also achieve much more accurate pointing with compared to magnetorquers because they're not dependent on Earth's magnetic field. Earth's magnetic field is actually like really non-uniform. It has a lot of like lumps and inconsistent, which can make the performance of magnetorquers vary a lot depending on where you are relative to the Earth. Reaction wheels, they pretty much always work the same. The problem is that they are hilariously expensive and they take a huge amount of your spacecraft in order to actually, fit them in there. But if you're in a high performance operation where you need accurate pointing, they're really the only true option you have. There's also the control moment gyro. I should say that usually reaction wheels come in sets of 3 because you need them to be orthogonal to each other. So one reaction wheel is able to act on each of the 3 axes, right? X, Y, and Z. Yeah, hold on. I'm going to silence my notifications because this has been pinging like the entire time. All right. Yeah. Now,
sorry, I was putting a meme.
Oh, okay. No problem, Flynn. Yeah, so usually you want 3 reaction wheels. Sometimes you have systems like this where there are 4 reaction wheels, not orthogonal to each other. And that's so that if one of the wheels fails, right, the other 3 can still pick up the slack and maintain control of the satellite. There is also the control moment gyroscope, which is essentially just one reaction wheel in an axis that you care a lot about. And I'll show you an example of what a control moment gyroscope can do a little later. But this is a more sort of unconventional take on how to do the control system.
Michael, have you shown the reaction sphere?
Oh, like the YouTube thing?
No. It's on Sat
Wait.
Search.
Oh, it is?
I mean, it's
Is there a
probably on
reaction
YouTube
sphere?
too. They have one, yeah.
Wait. Oh, I was looking at this. Oh, so it's just like a ball in the middle,
It's just
isn't
a
it?
ball. It can rotate any way.
Man, has this thing flown in space?
I don't think so, but potentially.
That's pretty wild. I don't know if I
Safe
trust that.
space, maybe.
Yeah, but like just a ball? That's kind of sketch. I don't know. Okay, I do want to take a quick breath and ask if there are questions.
No question.
So,
Sorry.
I just have one question on like magnetours versus reaction wheels. So like, let's say I wanted to rotate the spacecraft like 180 degrees. Like, how long would that take using a magnetorquer and a reaction wheel, respectively?
Um, okay, so like 180-degree turn, like magnetorquer versus reaction wheel.
Compare.
Wait, so sorry, you were breaking up a bit there.
My mute button was like going wild.
Oh, okay.
Sorry. I just wanted like what's like the comparison in speeds? Like does it take like a magnetor like hours to rotate in the right direction compared to like a reaction wheel which gets you in seconds, or is it more like minutes to like minutes?
Yeah. So the unfortunate answer that is the most true is that it depends. But the answer you actually want is probably that I think top of my head, like the back of the napkin calculation says that a 180-degree slew out of a beefy magnetorquer is probably going to be on the order of like, a couple minutes, right, to complete that maneuver. Actually, this is a great opportunity for me to go to the Bronco Space YouTube channel. Give me 1 second, guys, because I just remembered that we have a video. Where is it? Here it is. Yeah, there it is. Okay. So this video that I have flashed up on the screen here, this is a 40 times time lapse, right? So 40 minutes of real time. This is our satellite. This is a spherical air bearing system. And right now, we have the magnetorquer going at full blast, right? And it is rotating the spacecraft. The spherical air bearing creates a essentially frictionless environment. Now, as you can see, this is a 40x time lapse. So real time is like 40 minutes and not very fast, right? Like this is not a speedy boy. On the other hand, you can actually just look up like CubeSat reaction wheel, I think, and it will show you something much more speedy. Let me see if this is a good example. Yeah, like you see the wheel turning here, and this is real time, of course. So okay, well the guy's like bumping it with his hand, but let me see. Actually, spherical air bearing, I think that's good. As you can see, I like to just do it live. CubeSat. Is this a good video? Okay, I don't really understand the system going in here, but it looks like this is about a 6U size CubeSat with some really beefy reaction wheels in there that I assume are actually torquing on the system. Yeah. So I would actually probably say it's fair to say that it is an order of magnitude like difference in speed going from the going from the magnet torquers to the reaction wheel. Does that sort of sufficiently answer your question? Of course, it depends on like the size of both. Like beefy magnet torquers could theoretically generate more torque and move faster, and at the same time, puny reaction wheels, are gonna move pretty slow. But yeah, I would say reaction wheel completing like 180 degree turn in like 30 seconds, right, would be quick work, and sometimes you can move even faster than that. All right. Any other questions?
Sorry, I was gonna say earlier about I don't remember what it was called, but basically just the spinning ball that controls things. Like, we're undergraduate developers. I feel like everything we do is a little sketchy.
Yeah, no, like for sure. If there's time, I might even I mean, yeah, like if there's time, I might even show kind of what like BroncoSat has cooked up, because it's a little. Oh, Chris is telling me to not. I think. Yeah.
Yeah, one of our like main problems that we're kind of working on right now, you talked a little bit about it earlier, like, if solar panels are a big part of your design, you might want to figure out a way to point towards the sun all the time. So attitude control is kind of like something that we're determining whether or not we want, a more just doing the permanent magnet that comes like with the fast bus, or just like getting an actual magnet torquer. And I guess I would like to hear your guys' thoughts on if it'd be worth it.
Yeah. So my advice as not a veteran engineer, but only a one-time CubeSat engineer, is it's actually trivially easy to include like a magnet torquer in your system, as long as there's sufficient foresight, right? Like if it's in your design from the beginning, then you can integrate one with relative ease, because it literally is just a coil of wire, right? We on BroncoSat have two torque rods and one open air coil. So the open air coil is just a coil of wire, right? Nothing else. And then the two torque rods are actually inductors. Like we went to a commercial manufacturer and said, make us an inductor in this size, and they did it. And now we have magnet torquers, and we just have to run the current through them to generate the magnetic fields. The problem, of course, though, is that there is a lot of back-end stuff that you need to include in order to make the control system actually work. Like we need motor drivers to actually send the current, right? We need sensors to sort of provide all the feedback for the system. And then we also need to build out all the software, right, to do the controlling. And that takes up a very significant amount of time and effort for the team. So you have to sort of really think about it, like, does it really add that much value to your mission? I think actually for most missions, the answer is yes. But then, of course, you have to weigh it against, like, is it a realistic thing for us to do? And the answer might be no in many cases where you're just trying to get something done kind of quick. The engineering saying is, of course, never let perfect be the enemy of good enough.
Okay, thank you.
Yeah, no problem. Any other questions at this stage? Oh, yes. Okay, so why did you choose to use one opener coil and two inductors as opposed to just three inductors? The answer is that was the only way we get them to fit. The open air coil is like this big, it's a bundle of wire essentially in a circle, or in our case, a rough square. And so it's relatively flat. So if you remember, right, back to your electricity and magnetism class, for us at Cal Poly, it's like 1520. The magnetic field generated by electricity running through a wire is a function of the number of turns times the current running through the NIA. Yeah. Wait. Yeah. It's a number of turns times the current running through the wire times the area enclosed by the wire, right? So you can move those knobs however you please in order to get the magnetic dipole that you desire. So when we have the inductors, there are a lot of turns. Like I think it's like 1,200 turns is how many turns we have on those inductors. The current is like an amp. But the area that it encloses is not very big. It's like, I don't remember how thick the bolt is. I think it's like a quarter-inch bolt, right, that acts as the core. So the area enclosed is very small. On the other hand, the open air coil, it's only in the neighborhood of like 200 turns, I think. And the current's the same, but we are enclosing a much larger area. I think 50 square centimeters with the open air coils. I'm probably less than that actually. So it's a balancing act, and you have to decide like not just what's going to give you the performance you require, but how is it going to fit in your system. In our case, we have these like two solid walls, right? Like six-sided cube, right? We had places to mount the Macatorcus 2 solidly on 4 out of 6 sides. But in order to get all 3 axes, the 2 sides that we did not have like somewhere stable to mount a rod to, we decided instead just to have the open air coil because we literally just glued it onto the wall with space glue. And that's a pretty sufficient way to get around that. Yeah. Does that answer your question, Michael? Cool. Any other questions, guys? Not all. Soldier onwards. Take another drink of water real quick. Okay. So once you selected your hardware, right? Oh, I didn't even talk about the determination hardware. I'll talk about determination in a little bit. We'll just focus on control right now. Then you define like then you define the determination and control algorithms. So like I said, it's not just the actuator you think about, right? It's also all of the software behind the scenes that makes the actuators go, you have to think about as well. Probably the one that you're going to learn very quickly, right, in the CubeSat space is this a detumble algorithm for magnetorquers known as BDOT. BDOT is kind of what you think it is, where you're basically taking the dot product of the ambient magnetic field compared to the magnetic field your spacecraft is able to produce, and you use that in order to get the difference down to zero, right? Like you're basically canceling out all of the rotational energy of the spacecraft until there's no change there. Relatively simple algorithm, and if you need to do like pointing or something like that, that's where you have to introduce something like the PID control, right? Where you will have a targeted value, be it in like Euler angles, which are your traditional like 0 to I think it's 180 degrees or negative 90 to 90 degrees, depending on who you ask. You have your Euler angles, right? Or your quaternion, which is, I've had it explained to me, which is like a vector, but with more terms so that it has like state information about the body as well. It's a vector that points in 3-dimensional space, but also has information that lets you figure out like what the faces of your object are. That's really kind of beyond the scope of this like introductory workshop, but Euler angles or quaternions, right, are the two sort of possibilities you have for, your control input, like go to this Euler angle, right, or go to this quaternion. And then the algorithm is what actually moves the spacecraft there. Yeah, and then once you sort of figure this stuff out, it's very important to iterate and document this process, right? It's very rare that like first right off the bat you're going to figure it out right away. Like for BroncoSat, we had like an original torque rod design, right? That we went to test, and then it just didn't really work as well as we wanted it to work. So we had to beef it up, add more turns, right? Um, we also had to, for example, like um, mess with our motor drivers in order to actually get them to perform the way we wanted to. Because the interface between the motor drivers and our flight computer was kind of wishy-washy, right? And yeah, there was stuff buying things I could do there. So here's the disturbance environment I was talking about. How much open source software can be reused? I think there's actually a pretty decent amount of open source software out there. I know that like BDOT, for example, is such a commonplace algorithm that you can find like BDOT source code just kind of floating out there relatively easily. And also like looking into like research papers, you can find the BDOT source code just like at dependent to the end of research papers. The issue, of course, with open source software is that, at least to my knowledge, there isn't really sort of an end all be all like software solution, um, because every satellite is different. And um, okay, let me just like quickly backtrack real quick. So y'all remember back here, right, where we were talking about like, you know, block diagram and like the plant, right, and all that stuff. So when you have when you're designing a control system, right? Like the gains, for example, that you stick in your PID controller, these are always going to be different depending on what your system is. Like let's say like, you know, you have like a really heavy spacecraft, right? Um, you can't just copy and paste like another control system onto that control system and expect it to work, right? Because if you take code that was meant for like a really light spacecraft and then impose it onto a heavy spacecraft, well, most likely what's going to happen is going to be like way under way it's going to way underperform, right? Because it just wasn't designed to work with that system. um this is sort of like a enduring problem, like with like just space mission engineering in general, where because every satellite is kind of designed like to spec and in a way that it's like we're just trying to meet like the specific mission requirements that are set out to us. It's hard to sort of just transfer like something that worked over here. We're just going to put it over here and expect it to work the same way. One of the sort of the up and coming sort of things that might make this a lot better is actually the use of like artificial intelligence or machine learning to have a control system sort of like tune itself. Because usually when you actually get down into the weeds of it, what usually has to happen is that you, like as the engineer, have to simulate the system, observe the system, and see, oh, you know, it's moving too slow, right? Or it's oscillating too much. Why don't I manually turn these knobs, right? And then we will get a result out the other end. Or, you know, if you have fancy pants software, the software can kind of do that for you too, right? This where the software will just randomly turn knobs until it gets to like a desirable result based on your requirements. Um, One of the up and coming fields is like the use of like an artificial intelligence to sort of learn to like use a control system the same way a human might, right? Where for example, you know, you get a car from the manufacturer, the steering is not always tuned to exactly everyone's preference, but you as a human, right, with your brain, you can figure out how to tune yourself, right, in order to drive the car effectively. Same sort of idea with the satellite, right, where one day maybe we can have the satellite teach itself how to do all that stuff. That was a really long-winded like tangent I just went on there. Does that answer your question, Kevin? I could have just said there is software and it's not really that reusable, and I would have probably answered your question. Yeah.
Yeah, that helps. Thank you.
All right. Yeah. I sure wish we could just copy paste stuff off of Stack Overflow for this, but it's a little more nuanced than that. Okay. Yeah, so this is a disturbance environment. I'm really just winging the flow of this here. So you have a whole lot of things that can contribute to like things that will disturb your spacecraft, like radiation pressure, drag, magnetic torque, gravity gradient. And the interesting thing is that you can actually use these disturbances to your advantage as well. For example, there unfortunately we don't have any Naval Academy folks joining us for the hackathon, but a couple years ago, one of their CubeSats that they flew actually used solar radiation pressure as a control method rather than like a magnetorquer or anything like that. What they essentially did is they painted half of their satellite in a bright white color and the other half in a more dark kind of black color. And what that created was a mismatch in reflectance, right? So that the solar radiation bouncing more off of the white side of the spacecraft actually induced a spin on the spacecraft. And they achieved spin stabilization purely based on solar radiation pressure. Maybe more famously, some engineers are trying to develop things like light sails, right? You might have heard of light sail and light sail 2 from the Planetary Society, where they unfurl this massive mylar blanket in space, and then just the photons bouncing off of it generate a force that can over time, speed up or slow down a spacecraft. Atmospheric drag just kind of is a drag. Like it can sometimes be used as a control method, particularly like you can use the drag to orient your spacecraft in what's known as like the ram direction, but using atmospheric drag is usually not really something that is ever designed for because it's highly inconsistent once you're in orbit, because atmospheric drag turns out to be at the incredible altitudes of space entirely dependent on solar activity. When the sun hits the earth and more vigorously, right, the atmosphere actually expands and creates more drag. Right now, we're in a legendary solar minimum, so there's actually very little atmospheric drag to work with. Already talked about magnetic field. Gravity gradient is something that a lot of big satellites use pretty often. CubeSats have tried to use gravity gradient, but to my knowledge, there has been no CubeSat that has successfully used a gravity gradient control method, mainly because like they're too small. Like there's not enough mass there to work with. The premise, though, is that if your spacecraft is very lopsided in weight to one end, the heavier end will want to orient itself towards the Earth. Imagine kind of like a pendulum, right? Like the heavy end wants to point down towards the Earth. Unfortunately, like again, CubeSats are kind of too small to really use gravity gradient, but some people have tried and unfortunately failed. If you want to look up the Firefly satellite, I think that's the most like famous example of that. There are some other sort of internal disturbances we run into too, right? Like CG uncertainty, right? This isn't a huge problem for CubeSats actually, because usually CubeSats aren't losing mass while they're operating. Like there's no propellant that's being burned or anything like that. So if you get a good CG on the ground, it kind of sticks. Big problem with reaction wheels is that they generally will experience friction, right? Which over the life of the wheel will introduce a small disturbance torque. And more importantly, can also sometimes induce failure in the wheels, which just leaves you totally shit out of luck. And the other thing with reaction wheels is that they can actually saturate, which is essentially when the motor is spinning so fast, it cannot spin any faster. And at that point, you just run out of control authority, right? Like the motor cannot speed up anymore. You can no longer, induce more torque in that direction, which is why you oftentimes need to couple it with like magnetorquers as well, So you can have like a counter torque that will allow you to desaturate the reaction wheel. Thermal shock, also not a huge problem for small satellites because they're small, but something to be aware of, which is when you come out of the Earth's shadow, the rapid thermal expansion that happens as a result of the sun suddenly hitting, the cold and dark spacecraft, can introduce like a little jolt that can be an issue for really sensitive missions. So here's actually an example of what like a really high level design for a ADAC system might be. Here, right, is an amazing PowerPoint sketch using PowerPoint auto shapes, where we have noted that there are externally mounted sun sensors. So this is where I need to acknowledge that there's also a determination aspect to attitude control, right? Where the spacecraft needs to be able to figure out where the spacecraft is. And more importantly, it needs to figure out where the spacecraft is pointing, right? Because the spacecraft does not have eyes, right? And then in the cold darkness of space, there's no like reference points. Like robot arm is just bolted to the ground, right? Like robot arm knows where robot arm is pretty much all the time, based on like its original location. But when the CubeSat comes out of the deployer, it will essentially have no knowledge of its surroundings or its initial state. And as a result, it needs to use external sensors or internal sensors to figure that out. Pretty commonly, you'll see magnetometers inside satellites. Pretty much all satellites will have a magnetometer because you can use the magnetic field to sort of get an understanding of where you are relative to Earth. And most, if not all, satellites will also have externally mounted sun sensors in some way because these can provide a state vector in the general direction of the sun. The premise here basically, right, is that you can understand like where the sun is in space and then locate your satellite using that, where you have sun coming in like this, right? It'll only trigger these two sun sensors. So therefore, right, the sun is in this direction and obviously not in this direction. And you can also sort of use more advanced sort of sensor fusion methods to really actually provide a shockingly accurate orientation for your satellite based on like these sun sensor these sun sensors. You can also use the solar panels. So here I've noted that these are dedicated sun sensors, which might manifest as like a UV sensor or like a photoresistive sensor. But some satellites will actually just use their solar panels, right? Because depending on the angle of incidence, right, that is the angle of the sun relative to the solar panel, the voltage or current, depends on how they're wired, of these solar panels will vary. And you can you can develop a model basically, right, where you use the varying currents and voltage in the solar panels exactly as you would use like the varying currents or voltage in your dedicated like UV sensor or photoresistive sun sensor. Yeah. So those are some like attitude determination things. I know Stanford, Flynn had to jump out to eat dinner with his family, but Stanford, they're trying to have an AI actually figure out like the attitude of the satellite just by looking at pictures that like a outward facing camera takes. So that's sort of like a new frontier sort of technology. Yeah. Now, also on this design, if we kind of go to the next slide, we also have some control stuff here, right? Where like as 3U satellite, we have a momentum bias wheel here, right? So this is, imagine just like one reaction wheel, right? Like in this axis. And so if it's spinning this direction or the other direction, it can induce a torque about the y-axis, assuming that the y-axis is like coming out of the page. And why you would want to do this is, well, one reaction wheel is less complex than 3 reaction wheels. And for a satellite like this, the example here is like this is a like Earth sensing system. Like imagine this is like a camera in here. And you want to like maybe track a position on the Earth, right? Magnetorquers don't have enough control authority to do that like rapidly. Like they can't make that relatively fast motion to track an object as it flies under the satellite. But a single reaction wheel in that axis can actually provide that like whoosh, like rapid slew as it's called. And then you'll have like magnetorquers just for controlling the other axes at a much more leisurely pace. Yeah. Oh, here's just some nomenclature, right? Like the velocity vector, right? By convention is usually positive x, right? That's the direction the spacecraft is traveling in. And then the nadir vector, nadir is directly down, right? So imagine like a line that just goes straight down from the satellite into the planet. And then zenith, right? If you encounter the word zenith, that is directly up, right? So straight out of the planet, directly up through the satellite. Here, I've also noted some like example control modes and then the control methods associated with them. So for example, when we come out of the deployer, right, there's an unknown amount of spin that is put on by the whole spring-loaded box thing. So we need to detumble with our magnetorquers and a little bit of gravity gradient helping us out in order to, stabilize the spacecraft. Then, right, we might need to do some earth pointing or horizon pointing to sort of orient the spacecraft, get it ready for, doing imaging or things like that. Then we might have like sun tracking, right? If you have to use deploying solar panels, when we need to charge the spacecraft up, we'll want to make sure they're pointed so that they're perpendicular to the oncoming sunlight so they generate maximum power. There might also be like ground target tracking, right? Where we're flying over a ground target and we want to maintain a fix on it as we fly by so the camera has a lot of time on target. It's also just desaturation, right? Because remember, those reaction wheels can get saturated. You want to make sure that you're able to desaturate them so you can still get that rapid maneuvering. And deorbit is actually a control mode that I think most CubeSats do not implement something for, but it's good practice to also have a deorbit control mode where if it is like all possible, you try to orient the spacecraft in a way where you maximize the cross-sectional area of the spacecraft. And what that does is it increases the drag and causes the spacecraft to fall out of orbit faster. It's just sort of like a best practice thing. It doesn't no one's gonna like prosecute you, right? Like if your spacecraft doesn't deorbit on time. But it is good to have some kind of end of life scheme just to keep like space garbage to a minimum once you're done with your mission. And yeah, that kind of concludes like the example portion of the workshop. Are there any questions at this point? Like, do I even have anything planned after this? Oops, discard. No, that's pretty much the end. There's a bit of control theory here, right? But yeah, this is pretty much it. You guys have any questions you want to bring up? Comments? I'd actually like to know if this like made a lot of sense or if it was a little too rambly. It's a lot of content to try and cram in this short amount of time. All right, got one great workshop. That's good enough for me, I guess. Yeah. Well, oh yeah, question?
What was that last actuator that you showed us? Maybe it was like momentum bias wheel?
Yeah, the momentum bias wheel.
It was like the last one that you showed us on that website.
Oh, the sphere. Hold on, let me. Yeah, like go sat search, actuators. Wait, it's like the reaction sphere, right? Or is that what it is?
Oh, no, so, yeah, the control moment gyroscope.
Oh no, just the control moment gyroscope. Yeah. Yes. What about the control moment gyroscope?
So how is that different from like a regular reaction wheel?
Usually, control moment gyroscopes are much bigger. Although functionally they behave exactly the same as a single reaction wheel. Yeah, like the nomenclature of control moment gyro just sort of differentiates the fact that it's used for a different purpose than the reaction wheel.
Okay, got it. Thank you.
Yeah. Any other questions? If there are not, then we'll probably just wrap it up here. And I hope to see you guys, over the weekend